Let's go.
Let's go. Welcome, everyone. It's 7 a.m. PST time and 4 p.m. Central European time. My name is Nabi, and we are very excited here to host you for the third session of DataForge Fireside Chats. It's the chat that me and Francesco we're trying to talk about different topics in data science and make them more understandable for non-technical audience, and at the same time having some critical conversations about the technology emerging in this field for technical audience. Today we are going to talk about object tracking, and we are going to talk about what actually you can't get from ChatGPT, because everyone nowadays is asking like a lot of questions from this tool, like how to learn about this technology or the other technology, or like learning different things in simple concepts. But today we are going to have a little bit of a high level conversation about object tracking and its recent development. Okay, the floor is yours. You want to start a welcome message, Francisco,
Of
and then we
course.
go for the questions.
Well, thanks, Nabi, for organizing this. It was very nice to finish the week with the fireside chat.
Yeah.
um, and indeed, yes, I'm very excited to share some of the methodologies that are widely used, adopted, and quite mature now about object tracking technology. A little bit of history, and of course some implications that this technology have in society, the human impact. Let's say that's probably what you were referring to when you said this is not no time for ChatGPT now. Let's talk
Yeah,
with you.
exactly.
Yeah, so yeah, let's uh, let's roll it.
Yeah, great. So let's start with the history and like the evolution of object tracking. I remember the very first time that I was kind of dealing with the same thing was those speed cameras, that they were somehow able to like capture our car's speed and like getting issuing us a ticket. So let's go
They
for
still
the
do.
history of object tracking to see like basically how it's coming from and what are the fundamentals of object tracking. If you want to, let's say, talk about this sort of problem in a more of a technical way, what are the fundamentals of it, and how in the recent years deep learning is helping for a better and also more accurate object tracking algorithms.
Yeah, I mean, first of all, sorry to disappoint you, but the car cameras are still working very, very good. So they will keep
Yeah.
tracking you on the highway in case you above a speed. Um, Fortunately, I would say there are, of course, many good implications and many bad implications about every type of technology, but more on that later. What I'm going to say today is, in fact, something that goes hand in hand with the models that we are, at least the big audience is used to deal with today, which is NLP, and in particular large language models. So, what I'm saying here now about computer vision and object tracking, in fact, it goes hand in hand with that.
Mhm.
All these things are all tightly connected due to one substantial common factor, which is indeed deep learning technology. And so when we talk about object tracking, in fact, we are
Mhm.
talking about a number of things, not just the tracking mechanism.
Mhm.
Uh, we are talking usually about, well, first of all, detection of an object, the object that in fact you would like to track later.
Mhm.
You first need to detect it.
Yeah,
Uh,
yeah.
then you need the tracking, and there is a very interesting literature about tracking algorithms. And finally, there is the association.
Mhm.
So, okay, let's start from the beginning. What is detection? Detection is identifying an object of interest in a scene, right? Be it a car, a person, a face, a cat. If you ever want to track cats. um,
Mhm.
and historically, there have been human beings creating features to detect objects of a certain type, right?
Yeah.
Then with deep learning, we had so before deep learning, we did a lot of, for example, edge detection, template matching. They were all
Mm-hmm.
classic algorithms to detect things and to transform, let's say, the pixel representation or a group of pixels into something, some kind of information that could have been used to indeed identify and detect a particular object. Then we had deep learning, and we realized that wow, we don't need to make our own features by hand. There is this convolution neural network. Usually, I mean, they were great and still are a great way to, in fact, generate these features
Yeah.
for you by just sliding in the image uh, and collecting or calculating features, so-called feature maps, and then using these features for whatever task you have at hand, usually
Mm-hmm.
classification.
Yeah.
Then we then we have the second part, which is the tracking, the actual tracking, and that's maintaining the, let's say, identity of the objects that you have detected over time as it moves within a video or
Mm-hmm.
a sequence of frames. And here, again, this is another very well-known task in computer vision. We
Mm-hmm.
started with the optical flow algorithms, with particle filters, even before that, Kalman filters. We still use these things, of course,
Yeah.
um, in combination, of course, with the deep learning features or deep learning based or extracted features.
Mm-hmm.
And finally, we have the third piece of the puzzle, which is the association. And association means matching the objects that you have detected across frames
Mm-hmm.
to maintain their identity. So what this means is that if you detect something at, let's say, frame one, let's say the car, Nabi's car, that is going fast, uh, then I know that.
Yeah. As a fact.
There is prior knowledge that
Yeah.
about that fact. Now, jokes apart, we detect the car, Nabi's car at frame one, and then we want to, let's say, follow and associate the car that we're going to detect at frame 2, 3, and 4, etc. We want to associate whatever we detect there with Nabi's car because it's the same
Mm-hmm.
car. Now, if we have only one car in the frame, that's easy. The problem is when you have multiple cars in the frame, you don't want to
Yeah.
mix things. So you don't want to mix the car of Nabi at frame one with someone else's car um,
Mm-hmm.
in the next frame. So that's the association problem. And historically, there have been two methods that I know of, in fact, two schools of thought, which is one goes under the name of a Hungarian algorithm,
Mm-hmm.
and that's a combinatorial optimization algorithm. Of course, I don't go into the details because it's like we need an episode only for that. But in case the people listening want to do some research on the internet, these are the keywords that, in my opinion, are a very good starting point.
Mm-hmm.
The Hungarian algorithm, and the other one is the multiple hypothesis tracking,
Mm-hmm.
which is a probabilistic data association algorithm for tracking multiple objects. So one, solves the problem with a combinatorial optimization, and the other
Mm-hmm.
with probabilistic approach, so more statistics and probability.
Mm-hmm.
Um, Now, these are the three essential tasks. So when you say object tracking, in fact, you are referring to this
To
at
these
least
three
three.
tasks.
Yeah, correct.
Yeah. Great. So, like, I think in terms of the evolution of the object tracking algorithms, we were like reviewing a paper last night, I remember, and like we found a good graph there. So, like, you want to talk about the graph? I can share it here. So, like, talking about the evolution of these algorithms and like how basically um, object tracking improved throughout the time.
Yeah, well, for sure. When it's if you look at this picture, you see that up to 2006. In fact, I remember even before, but anyway, we already had some, of course, neural networks back in the days, 2008. In fact, even before, even in the 90s, we had neural networks. The problem is that we didn't have enough compute power to process they were unusable in a
The
way.
network,
So
yeah.
yeah, so running this, there were GPUs, but not as powerful as the ones that we have today. So um, also the libraries, we didn't have enough libraries and frameworks, software frameworks to deal with neural networks. And so researchers back in the days, as I said, were using what we call now the traditional algorithms. And as you can see from, of course, it's quite a confounding factor, the fact that in 2001 there's not so much literature, and then all of a sudden after 2014, 15, there was some kind of explosion of methodologies. But that's essentially due to the fact that deep learning
Yeah.
kicked in, and you see that there is a flipping point there,
Yeah.
due to two important facts, which is better hardware and better data and more availability of data. Because computer vision has always been like the one of the most hungry algorithms, that require an humongous amount of data. And we'll discuss about that with the data set diversity and data augmentation.
Yeah.
But until that point, we had the concept of deep learning, not deep learning, we had the concept of neural networks. Okay?
Networks, yeah.
We didn't have the concept of deep learning because we didn't have the hardware that could calculate in a decent
In a fast
time.
way.
Yeah, in a fast way, all these things. But of course, we knew that we should have stacked up many layers. But it was like, yeah, when you
How to
propose
solve
these
it.
things, when you propose these things like in academia, there were theoretical things. And when you looked at people like, hey, I would like, that you can have like non-linearities by increasing the number of layers in a neural network. So yeah, sure, theoretically it's possible, but I don't have the computer to do that,
To do
And
that.
now it's like, now we laugh about it, but we were like, as they chop your legs and they ask you to run, it's exactly that. We had the
It's how it
theory.
looked like before 2014, before having good GPUs around us.
Exactly. And then of course
Great.
we had, and then the very last thing that I want to add is that when you look at the literature, when people realized that more deeper networks could in fact were very good at generating the features for them, they stopped making features manually, and they leveraged the deep network to do that. And when I said this was hand in hand with the large language models in NLP, which is a completely different sector or field, I want to reinforce this statement because that's exactly what happens in linguistic, for example. In linguistic, they were essentially creating their own features for language and text until they didn't have to do that anymore manually because deep learning kicked in, and we realized that the features generated by deep learning were good enough at the time, and now they're actually great.
Yeah, yeah, exactly. Speaking of, you pointed really important fact here that like basically these algorithms, like object tracking algorithms, are data hungry, and they need intensive amount of data for like training phases and basically to make sure at least the detection works well, and then like association phase is also having the right performance. Like speaking of data augmentation and data set diversity, we've seen also like one of our sponsors, Parallel Domain, they're also specialized in synthetic data and producing data from their generators. What's the role of data augmentation in this field? Can you elaborate more on that, and how basically these methods are benefited from a augmented data and also like a diversity in the data set? I think that's really important fact to consider that we can't collect like thousands of like images and videos, and they're also heavy. And what's the solution here? Like, is it just the documentation, or like there will be some other kind of let's say
Yeah,
bypasses here as well?
sure. So, of course, this question has an answer that many out there should expect. Of course, data augmentation and data diversity always play not only a crucial role in machine learning, but a fundamental role in developing robust algorithms in general and robust models in general. Even more so when it comes to object tracking models. So the problem of object tracking models is that, well, in fact, the problem of object detection models is that the object that you want to detect is never, unless you're in a lab, it's never there alone. Hey, I'm a chair and there's nothing else around me. you know,
Yeah,
if you are detecting a person, detecting a person in a room with a green background, that's ideal.
that's ideal.
But
Exactly.
detecting a person in a crowd, or while the person is moving, or while the person is getting closer to the camera for which it starts growing, zooming in. It's equivalent of zooming in for a camera,
Hmm.
or that's called size change, or when light changes, you have different light settings,
Hmm.
um, or you run into a shadow, and all of a sudden the camera stops detecting that person because it's in the shadow.
Hmm.
So you see, there are many complications and challenges when you track things in the real world,
Yeah.
um, and so that's where first the first versions of the object trackers and object detectors that we know didn't handle these challenges well.
Yeah.
And so what we realized was that the training data needed to be augmented in a way. And how do you augment data for let's say, an object detector? Well, there are many ways. You can start perturbing the data that you have. And when you perturb the data that you have, you start generating additional data that come out of the perturbation. Perturbing could mean, the classic flipping, rotating, scaling, um, but
Resizing.
even yeah, but even masking out some
Hmm.
pixels, mimicking some kind of error in the communication, or
Hmm.
the camera that breaks. Even putting layers. I've seen people putting layers in front of the cameras, like a broken glass or
Yeah.
whatever, to perturb the image and keep training the algorithm under these critical circumstances.
Circumstances.
And then there has been also more sophisticated ways to augment data. For example, when you can you can, for example, obfuscate a particular part of the scene, or you can do occlusion on a particular person, or you can do partial occlusion, which is also another thing that we do all the time. For example,
Yeah.
you know hiding a piece of the car and
Hmm.
still
Hmm. Yeah,
and
I've
still
seen those like data augmentation
yeah,
methods.
and still seeing if the algorithm detects that as a car. It should, and now deep learning does that very well. You don't need to see the car 100%. You can know it's a car by looking at
Hmm.
a fraction of the entire car. And then there is even more sophisticated solutions, which is probably the one you mentioned, parallel domain, which is creating 3D models of the world. So 3D scenes, like there are graphic designers, and then uh, creating pictures, putting a virtual camera in the 3D world, like a video
Hmm.
game,
Hmm.
and essentially create worlds. This is
Hmm.
very useful for example, autonomous driving data sets, in which you
Yeah,
want to
exactly.
create scenarios that are dangerous to replicate in reality. For example, hey, let's see what happens when you cross the street and the car is coming 100 miles per hour. You don't want to try that in a physical environment. You,
Yeah,
you would
exactly.
like to simulate that first, hopefully. So these are the situations in which data generation and generative models together with 3D models have being so useful to create these augmented
Hmm.
data sets, and creating also data set diversity, which is the number one uh, reason to have a more robust model, especially in deep learning.
Yeah, exactly. Um, it's really important to know like basically what are the techniques and what are the problems that we are trying to solve with data augmentation, and what type of problems like what type of diversity we need to add to the images and to the training data set. Uh, I had one question, like basically it might be, I mean, the positive side of it might be obvious, but like, uh, we've seen a lot of use cases by object tracking in different industries, from health industry to like production industry to like let's say security, and like basically what are the positive impacts of these algorithms and these let's say technology. We are going to go definitely deeper to the negative impacts, and we're going to talk about a lot of privacy concerns around these let's say technology. But like what are the positive impacts of this technology, and how can they make our world is a better place, I mean better place to live?
Yeah, I mean, it's that's a very good point and a very good question. The thing is that all types of technologies have some sort of positive impact on humanity and society. It's up to us, not to not to abuse of that
Hmm.
technology for something else. That's, I think that's quite. I'm stating the obvious, but unfortunately, many out there don't grasp. Seem they don't grasp this. I'm
Yeah.
referring, for example, to the last attempt to stop doing research in artificial intelligence, because I mean, this is really time to laugh, because this is really one of the biggest nonsense that I've ever heard in my
Yeah,
career. And
I believe that too.
it's like, oh, this is too good. Let's stop doing research. I mean, it does make sense. So with this said, um, my opinion on that, and I close the critique.
Conversation.
It's like, if you ever had stopped doing research on that, please bring it back, because it's nonsense. Stopping doing research is one of the most damaging things you
Strategies
can
that
do
could be
to.
there. Yeah.
Yeah, and it leads you nowhere. It's the same as saying, the concept of the car is so good that it can be used, it can be misused, and it becomes very dangerous
Hmm.
thing. So let's stop producing cars. I mean,
Cars.
does make sense, right? Eventually, what you would like to do is, let's start regulating cars,
Hmm.
which is exactly what they did 100 years ago. That's
Yeah.
why we have a code, and you need a license, and you need to go to school and learn the code and learn the rules and respect them. Uh, it's called regulation. It works for cars. It will work for artificial intelligence. It works for jets, audio systems, or discotheques. Everything is regulated, because we are a society, and there are
Yeah,
rules, if
exactly.
you like it or not. Now, what are some positive impacts of object tracking technology? Of course, there are many. It depends where you are adopting this
Adopting it.
technology. If you are in manufacturing, for example, quality control, or improved safety. I
Hmm.
worked for there was one very interesting project for InsurTech,
Hmm.
in which we could track essentially workers on site, and detect if, for example, they were wearing a helmet, if they're wearing protective shoes, um, if they were smoking very close to an area with inflammable material, etc., etc. And so,
Hmm.
of course, that is like, you need to detect people, you need to do tracking, you need to do a lot of those computer vision technologies that I mentioned before. uh, you improve safety 100%. On the big numbers, you could even see that the numbers were playing in our favor. Like, with the presence of an algorithm, with the presence of a camera or a set of cameras doing 24-hour monitoring
Hmm.
on manufacturing, on industrial plants, uh, you improved the safety. Less people got injured, and the safety overall, also for the insurance companies, was better.
Yeah.
And enhancing efficiency in various industries. Again, transportation, optimizing routes, reducing delivery times. We became all of a sudden lazy enough to invent this new job, which is, the delivery companies. But essentially, okay, it's an evolution of society. But without computer vision and tracking technology, these people would have a harder time. Increased accessibility. Think about
Yeah.
healthcare. Um, in the clinics, I've heard of some projects where they use computer vision algorithms to monitor patients, usually elderly, old people, old patients, who need to be monitored 24 hours, and see, for example, using
Motion tracking. Yeah.
motion tracking, object pose tracking, detecting the pose of the body, and inferring if the person needs help, because maybe these people are far from the red button, or they just can't, or they're paralyzed, or they're in a hectic situation in which they need
Yeah.
a monitoring system. So as you can see, we can all benefit of object tracking technology. Now,
Yeah.
if you use the object tracking technology to spy on people, or you cannot handle the data that you collect in a regulated way, well, you are diverging from,
The
not from the
positive
technology,
aspect of it.
from the positive impacts, but because you are abusing the technology. It's not because the technology is bad per se. That's what I want to say. And so here I can mention, for example, the privacy concerns. When you say to people, hey, I will put cameras in the cities and I'll start tracking people, they will raise an eyebrow and say, I don't like that. I have privacy concerns, right?
Yeah, exactly.
Which is true. If you start sharing that data, or if you cannot, let's say, if you use this data for other purposes, then the security, for example, concern. But when someone tries to rob you, I assure you that you would like that someone to be tracked,
Be tracked
wherever
for at least
he
5
or she is
kilometers.
going, and eventually catch him and secure him to justice. I don't know. I'm just creating a scenario for an urban setting in which you have a coverage of the city with cameras, that you go to the supermarket, you go to groceries shop, and you feel like someone is tracking you, which is true. Now, if the local government is not abusing the technology and taking the right and regulate and let's say following the regulation of GDPR, of all the privacy concerns that might arise when you deal with the images and tracking people, if that's regulated, I don't see why we should not accept and adopt technologies like this one.
Yeah, exactly.
Of course. Yeah, sorry, go ahead.
You go. No, you go ahead.
Yeah, no, I was saying probably another bad negative impact that I have on top of my head is bias and discrimination.
Exactly. That's what I wanted to add. Like, what if the object tracking algorithm detects someone committing a crime, but actually they're not? So how to deal with type 1 and type 2 errors, with these false positives, false negatives? And let's talk about this, because that's where these algorithms are starting to like apply their bias and discriminating people's right?
Absolutely, and it happens all the time. When I say it happens all the time, I'm referring to the private models that are not trained, that you don't find on Hugging Face and all these big massive models, but they are stuff that is like regulated, like models that are controlled by an entity. And so what happens there is that you can have, these models are almost always biased because they are of a narrow domain, okay, specialized in, they're not general purpose models, but they're models specialized in a particular type of tracking, with certain characteristics that are usually very local. Now, what happens there is that, of course, the algorithm is biased. And of course, you are opening the door to a discrimination issue when you
Yeah,
put that
exactly.
algorithm in place. And I'm giving a very brief example, completely created by my imagination. Though I'm pretty sure it happened. Imagine, a black person gets tracked. Okay, you have an algorithm that has been trained on let's say Caucasian
Yeah, Caucasian
people, Caucasian
dominant.
population,
Yeah, that's it.
because the local setting where they wanted to deploy the algorithm was indeed for 90+% Caucasian.
Yeah.
Now, what happens when you start mixing the population and some Asian, African American people come and they get tracked and they get in front of the camera, right?
Hmm.
Well, it could happen that the algorithm stops detecting because, of course, it doesn't. It's not been trained on that particular
Mm.
setting, and so we miss the detection, okay, for that particular individual. Now, to the people we are detecting, we are also, let's say, enhancing and improving some kind of social
Services or like,
services, exactly. Also, so they can enjoy these benefits of being tracked, while
and
the
also
others
model learn
do
them
not.
better as well.
Exactly. While the others do not, they cannot enjoy because they've not been detected in the first place because of an error or a bias in the algorithm, in the model.
So you
The
say
model,
even you say even not detecting is also kind of discrimination.
yes, because you cannot track something that you cannot detect
Hmm.
in the first place. So that's you're downhill towards discrimination. This is a discrimination problem, if you
Yeah,
think.
exactly.
Um, that starts from a technical issue, which is statistical bias. And so you
Hmm.
see how you're moving from a very technical conversation that is statistical bias to something that has a negative social impact, which is discrimination. Now, that's what I'm saying. Why I'm saying these things need to be regulated. We need, for example, we've been discussing this for years, and still we don't have a standard in the
Yeah.
way we produce certain models. We don't have a way to, for example, reproducibility.
Hmm.
We don't have a way to um, um, uh, understand what is the population of the training data that you train this model with, right?
Yeah.
What are the specification of the training data? Now you're using ChatGPT. Everybody these days are using ChatGPT,
Everybody
but
loves it.
nobody's telling us, nobody's telling us what data, except for the article that OpenAI has been writing and say, we use Reddit, we use Stack Overflow, I think, or whatever, and Wikipedia and many other blogs around. But in fact, they don't provide references. They don't know. It's a pool of things that all of a sudden loses track of where did this data come from. This answer that you're giving me in this chat, where does it come from? Where did you learn it from? And it's impossible to do that.
Hmm.
Uh, that's why also in generative models, artists are raising an eyebrow.
Criticizing it. Yeah.
I think I've seen this before. For 60%, this is mine, and for another 0 point something percent is of
Hmm.
another million people out there. Um, do you have a way to claim it's mine? No, because the algorithm ignores completely the source where that answer comes from. Um, that's reflected also in object tracking technology, in computer vision, object detection, and every time these models fail or are fully biased, well, that's exactly the same problem that you find everywhere.
Yeah, exactly. That was a really nice transition to like basically positive and negative impacts of these algorithms and uh, talking about like object tracking and knowing that as soon as you head out from your building, even if you're heading out from your apartment, there isn't any blind spot for you to being tracked like for maybe 5 kilometers, 6 kilometers, 10 kilometers diameter from your place.
Yes.
It's really scary. Like you just start like heading out from your place, and there are cameras that they are on overlaying each other's, let's say, uh, diameter, and then you're like, okay, what happens if a government, or let's say an authority, wants to install those cameras? And that's a lot of point about privacy concerns, and then we need to actually think about regulation, not pausing the AI research saying, oh, this is too good, this is too dangerous, and let's not do it.
Yes. No, absolutely. This is not a technical problem. This is a legal problem. We cannot solve. There is nothing that technical people can do anymore, except
Yeah.
enhancing the algorithms. The algorithms are doomed to become more and more powerful because there will always be more data. There will always be more, better techniques, better hardware, faster hardware.
Hmm.
So these things are doomed to improve,
Hmm.
100%. What we don't know yet what's going to happen is like, will we be fast enough to regulate these things? That's the
Yeah,
big problem.
that's a big problem. Exactly. Good. So that was a part of conversation that I really wanted to like hear your opinion on that, and see like basically what's the solution out there to overcome the negative impacts of these technologies. Well, they are built for, let's say, positive impacts. But let's say someone here wants to implement an object tracking engine, and they're looking for some libraries or some methods in object tracking. Um, what are the top, let's say, five or like top three methods in object tracking, and how they compare to each other with their performance? And if you want to measure their performance, what is the right metric to do? Like, I mean, some of these object tracking algorithms are basically classifiers, and like with classification, oh my God, you have a millions of combination of metrics to combine and like measure accuracy of models.
Yeah,
So like, what are the algorithms and how we can measure them? And that would be the question before the final question, which we are going to cover some future stuff and talking about
sure.
some future of these algorithms.
Yeah, so there are, in fact, there are probably four or five of the most widely adopted methods that the literature has been um, collecting so far. Now, of course, going into details of all these methods one by one is going to be a very technical and tedious conversation, especially because uh, you need to write down formulas and algorithms, in fact. But I will try to summarize. Of course, this is not the right place to have a lecture about sort, deep sort, and all the other
Yeah.
methods that we have. But I will mention some of them, and I also mention some keywords. Again, I think what is important out of this conversation is that after this, if you are interested, you go online and you search for whatever you are
Yeah.
interested in,
Yeah.
and then you expand.
That's the original purpose of this call.
Yeah, that's pretty much the spirit of the podcast. For those who know, I mean, those who know, they
Yeah.
know.
Yeah, exactly.
um,
If you know, you know.
if you know, you know. Um, so, well, the probably one of the simplest one is SORT, which stands for Simple Online Real-Time Tracking,
Hmm.
and this is it's pretty efficient. It uses a combination of motion models, Kalman filters, and the Hungarian algorithm, the combinatorial algorithm that I mentioned, to create the association essentially between objects detected in a frame and the same object detected in the uh, subsequent frames.
Hmm.
And the beauty of SORT is that it's so simple that it can operate in real time, and it's also very fast. Okay,
Hmm.
but it has problems, as always. Like something that is fast is not accurate, and so
Yeah.
usually, it has problems with occlusion, um, and also motion, if I remember well. So that's why they moved to something a bit more sophisticated, which is deep sort, an extension of sort, that incorporates so-called deep appearance model for object detection and tracking.
Mm-hmm.
That is essentially using a neural network to extract the features from the object bounding boxes. The object bounding boxes are, I've ever seen when you have an object detector or a tracker, you are the person that is being tracked, you are in a rectangle, usually
Yeah.
red or green, depending if you're the good
Yeah.
or the bad guy. and and that's essentially what it does. Like it uses a neural network to extract the features from the object bounding boxes, and these are used to associate and track objects across multiple frames.
Mm-hmm.
And then we have the MOT family, MOT, which stands for multi-object tracking. And here you
Yeah.
have the fair multi-object tracking, or fair MOT, and trans MOT, which is the one that is using a transformer.
Oh, okay.
And that's also a quite interesting one, because it uses transformer and also the concept of self-attention mechanism. So you
Mm.
see, these are all things that come from, we have seen these things in NLP. Okay, we
Yeah.
have seen these things in natural language processing. They are very, very coupled, very much coupled with computer vision algorithms as well. Why? It's because we are using the same models. We are using deep learning.
Yeah, we have all the same sort of like sequential concept over there. So like, why not?
Yes, these things go hand in hand all the time. And the last one, probably the fifth one, I don't know, I lost my count, but byte track, BYTE, byte. And byte track is also lightweight. It's also very efficient. And it uses a lightweight detector and then tracks again whatever you detect across frames using
Mm-hmm.
a model which is it's a motion model. So it
Yeah.
copes very well with things that move. Now,
Yeah.
if you want to go, I understand that from how I summarized this, I hope I did a decent job summarizing this, but they sound very similar to each other. And that's because there is at least 3-4 papers for each of these models
For each of these models.
to read, right? And there's of course the first paper that introduces the model. There are at least 5 different papers that you have to read. Then if you want to expand, you need another 5 or a dozen papers. So who am I to summarize a dozen paper in like what? I'm speaking since 3 minutes or less.
Yeah.
It cannot be done.
Definitely out of our limits.
So what you can do, however, is understanding what could I use where, right? So for example, sort. The sort algorithm performs well it's a simple model. It's very fast. It performs well in simple tracking scenarios, low object densities.
Mm-hmm.
For example, a car that is not so much traffic. But if
Yeah.
you are starting tracking people in a crowd or complex scenes with moving backgrounds, forget about sort, right?
Mm-hmm.
You probably would like to use some kind of deep sort that performs better in scenarios where there is occlusion, where there is appearance change, but of course requires more computational resources because there is a neural network
Yeah,
underneath.
a neural network running back there.
Now, for example, again, I'm an engineer. Where can I use these things? Well, it depends. If you are putting an object tracker on a camera that is in the city, there is a very small device, you don't have a lot of compute power, okay, but you still want to track best effort, what is happening in the streets.
Yeah.
Well, probably you have to go, probably sort is your only option.
Yeah, exactly.
Unless you can afford a powerful machine that has to be powered as well. Maybe you want to do it with solar, and you don't want to do that because it absorbs a lot of the GPUs cannot be, most of the time it's very hard to power that stuff with solar only, especially in Belgium. There's no sun even today. So there are some practical constraints that you need to consider when you use algorithms of this type.
Yeah. Mm-hmm. And let's talk about metrics. I think we have a couple of minutes to talk about metrics and then the future of object tracking, like where we see like this technology is going. What's the metric? What's the right metric? How to pick the right metric in
Yeah, it's
like
we are opening another
comparing the
big.
performance? Can
There
of
is another
worms
big,
here.
a big. This is an episode by itself, but okay. Again, you're putting me in a difficult situation now. So there is, if you Google or if you chat GPT, should we say that? Is it a verb already?
Yeah, it should be ChatGPT that please.
It doesn't sound right. But anyway, there is multiple object tracking accuracy,
Hmm.
MOTA,
Yeah.
and there is IDF1, uh, which is an F1 score, essentially, statistically.
Hmm.
Uh, Now, if you look at MOTA, uh, there is a formula. I'll try to summarize, to explain it here. You consider the false negatives, the false positives, the number of identity switches, that is
Hmm.
the objects that were assigned to the wrong track,
Hmm.
and the total number of objects in the ground truth. So you need all this information to calculate a mode. And the formula goes like 1 minus the false negatives plus the false positives plus the number of switches, everything divided by the number of objects. Okay.
Oh, okay, okay, okay.
So it's extremely hard to calculate this thing
Yeah.
unless you know exactly your data set. You know your data set
Hmm.
very well, because when is it going to happen that you know exactly the number of objects in a scene? It's when you know the scene very well, or you augmented your data set very well to include this information.
So why do I
Um,
want to learn it if I know the exact number?
yeah, you need manual
Labeling.
augmentation, manual labeling, and manual augmentation, of course. If you think that these things are magic, forget about it. Like there is still a lot of humans behind these things, even behind ChatGPT. Don't forget there is reinforcement
Hmm.
learning with human feedback. We said that in another episode of the show. I
Yeah,
highly recommend to follow to listen to that.
I'm gonna pull
Um,
up the episode as well. You go ahead.
yes, it's because people think that these things are magic. They're not. There is human beings behind doing the probably one of the most boring part of the job. Then we have IDF1. IDF1 is it's essentially, if you speak to a statistician, it's going to say, get out of here. This is F1 score. And it is. It's two
Hmm.
times the true positives divided by two times the true positives plus false positives plus false negatives. So, okay, you will never remember this. What you have to remember is that this metric takes into account not only the false positives, like
Hmm.
the false alarms that your object tracker generates, but also the false negatives,
False
which is
negatives.
the missed objects. Okay,
Yeah.
uh, and so by looking at that, you say, okay, well, these numbers go from, of course, from 0 to 1,
To
and
one.
you measure this thing. One thing that I want to say is that there is a very nice book by damn, I don't remember, but it's about lying with statistics. Okay, if you Google that
This is
again,
about metrics.
so it's very easy to lie with statistics. Can you get it for me?
I'm searching it right now. How to Lie with Statistics by Daryl
How to lie?
Hoof.
Yes, that'll have, yes,
Yes.
1954. That's it.
Yes, that's it. Yeah, that's it.
So that book is like, it's actually not very, it's like very very small book, but it was a slap in the face. It's 140 pages. Okay, but it was a slap in the face, like, and that's like an evergreen. Like statistics is as old as a century, and it's still, exactly, and it's still very very modern. I highly
Yeah.
recommend to read that book. So what I'm saying here is that many times uh, researchers, not all of them, have to be honest, the malicious ones, they use the metric that is more convenient for them to show how good their new
How
methodology is.
good and how new is their
Right.
methodology, but in fact, they're missing.
So
lots of
when you
things like that.
see, there is kind of an heuristic. When I see that a paper is not reporting at least 4 of the different metrics that we know,
Mhm.
I don't believe that methodology. Yeah, because there are so many. You go to archive, there are hundreds of papers every day.
Yeah.
I do 3 things: abstract, methods, and then the benchmarks. If in the benchmarks I don't see the table with at least 4 records with 4 different metrics that I know,
Mhm.
I don't even bother looking at the other parts of the paper. I skip it. It's trash for me. And so fortunately, there are many good researchers out there who know this, and they report everything, all the metrics, because an algorithm and also the type of data that you are using for training can, let's say, benefit one metric instead of another. And so it can be great with MOTA and terrible with HOTA, which is another thing,
Another
higher
metric.
order tracking accuracy.
Yeah.
Or it can be terrible on the F1 score.
Yeah.
So these
Exactly.
things can happen.
Great. Thanks for scratching the surface for the metrics. We know that it's really
Oh yeah,
hard
very
to
much.
honestly combine just the different trajectories in metrics, talking about independence, like accuracy, sufficiency, and separation is like really, really hard in the context of classification. While we are inviting our audience to ask their questions on LinkedIn Live, feel free to ask your questions. If there's any question popping up, we'll answer it. And at the end, I think we have a minute to basically not talk about, but basically talking about, like, basically wrapping up about how do we foresee this technology and the future of this technology and the future advancements of this technology.
Yeah, for sure. Well, first of all, I want to invite, if we don't make it here in the chat, we have a Discord channel, and everybody's welcome to join. There is a link that you will find on the official website, datascienceathome.com. That's a very nice place to indeed engage in conversations with the other followers, with ourselves, with
Mhm.
Nabi, with myself. It's always good to meet you there and discuss later. With this said, there is a natural evolution in the technologies that we are dealing with today, and this is again a very personal opinion. I hope it makes sense to you, and it does make sense to me. We'll see in a few years what happens, but it's not a matter of being right or wrong. It's just what I expect,
To
for
happen.
technology to happen and where to go. So I think that edge computing and real-time tracking are
Hmm.
very much coupled with each other. And we have seen this already in some industrial setting in which you need, for example, zero latency. And so, of course, you
Hmm.
cannot send your stuff to the cloud, process it remotely, and send back the result, because the object, the
The
item that
car
you're
is
creating,
crashing right now.
the car is crashing. Exactly. So autonomous driving, it's in fact it's the
Completely edge.
emblem of real time and edge computing. Uh, so I expect that these things would go hand in hand, and also because that would solve or partially solve the problem of privacy, because you don't have to send the video footage somewhere else, but you can do everything, for example, on the device, and the device can be a device that can be reset, for example, once it does the job. It can be even a disposable device,
Hmm.
right? That would destroy all the logs and delete all the uh, confidential information, or personal identifiable information, so-called PII, which is exactly what the regulators are afraid of. Um, Another thing that I see from a technological perspective is multimodal tracking.
Hmm. Yeah.
So, and this is important to me because We have seen already with ChatGPT, GPT-4, multimodality, which is the
Yeah.
capability of having, chatting with text, but also put some images in the mix. And who knows, maybe with GPT-5, we can put videos and other media, maybe
Yeah.
GPT-6 or 7, right? Um, so what I'm trying to say here is that I see analogies in this due to the fact that multimodal tracking to me means that you no longer use cameras, or you use cameras together with other sensors,
Mhm.
LiDAR, radar, infrared. These are
Yeah.
all sensors that come from the 80s and 90s, very mature technology, but they have not been used in combination except probably for military applications.
Yeah,
Uh,
exactly.
so was the GPS used by military application,
And
and now
they've
we
been
have it on every
expensive
phone.
too.
No, LiDAR still, if you want, a small device, but radar, infrared, definitely not.
Oh yeah.
Um,
Yeah. Yeah.
so, and how can they help? Well, these things can help. For example, when you have challenging scenarios like low light conditions.
Hmm.
Okay, we have good cameras now, but you can have a way better camera if you enhance with the infrared, an infrared sensor, and a radar or a lidar sensor, because low light conditions plus occlusions plus dynamic environments, like things that move very fast,
Hmm.
there's no camera technology that allows you to uh,
Hmm.
to to accept the challenge. A combination of sensors, that's what allows you, which is pretty much what the human eye, how the human eye works. The human eye is not one sensor, it's multiple
No.
sensors, and then that information is sent to the brain, which is, of course, there is multimodal. We are multimodal, I assure you.
Yeah.
um, Another thing is, of course, on the and we spent a few words already on this, interpretability, explainable AI. These are all terminologies that we have seen in other fields, other contexts,
Yeah.
even more so in the context of object tracking and
Hmm.
object detection algorithms as well.
Yeah, it's really interesting seeing like how these technologies are moving forward and what are going to be the new, let's say, chapters. Multimodal tracking. It seems that it seems the feasible future for this technology. Great. I want to thank you and thank our audience for attending today's call. We were a little bit over time, but of course, as always, we are going to post our content to our YouTube channel, to our website, to our social media, so on LinkedIn. So feel free to follow that and just go through it on your pace. We threw a lot of jargons here to your face. And so if you are basically interested in this technology, feel free to go for it. And I think at this point, if you don't have anything to add, we need to call it a call and wish everyone a very nice weekend, right?
Indeed, it was a pleasure, Nabi. Thanks again for organizing this. And
Yeah, thanks for making this happen.
yes, and it's always a pleasure to share whatever I can with a community. And again, I renew. We have a Discord. We definitely love to continue the conversations there. Technical, non-technical, personal opinions, the projects you're working on. We're always welcome to hear what's your story, and maybe we can collaborate. Who knows? I mean, this is
Yeah.
a fun way to collaborate by
Exactly. That's actually where I started. So I shared the Discord link in the chat. So feel free to follow our Discord channel as well, and wish everyone a nice weekend.
Thank you.